In this video, we will discuss reaction rates and the effect of concentration on them. We will introduce a method, the initial rate method, for determining rate equations. Also in this video, we will need to concentrate on actual scenarios for this information to make any sense. So we will be integrating problems into our discussion of concentration and reaction rates. There are four important factors which affect rates of reactions: reactant concentrations, temperature, catalysts, and surface area. This video will discuss how rate of reactions change when the reactant concentrations change. First of all, reactant concentrations. What happened to product concentrations? Product concentrations do not matter in the initial rate of reaction. This is because we will assume we start a reaction with just reactants. The products have not been formed yet. Since we are looking at initial rates, the concentration of the reactants are the only ones that will change at the beginning of the reaction. In general, rates increase as reactant concentrations increase. This makes sense. We have more reactant particles to collide to form product, so the rate of change will increase. But this does not tell us the extent rates depend on reactant concentrations. The extent rates depend on reactant concentrations are determined by reaction orders. These reaction orders are experimentally derived. They are not related to the stoichiometry of the reaction or the coefficients in the balanced equation. Usually, they will need you to give lots of information about initial rates and concentrations of the reactants to solve problems of this sort. For example, we have this reaction for the formation of NO2. O2 gas plus 2NO gas results in 2NO2 gas, and we have this data describing this reaction. We see that if we leave the concentration of NO the same and just change the concentration of O2, the initial rate of reaction increases. Also, if we leave the concentration of O2 the same and change the concentration of NO, the initial rate of reaction also increases. We conclude that the initial rate is proportional to the concentrations of O2 and NO. We define the rate law as rate equals a constant K, called the rate constant and represented by a lowercase k, times the concentration of O2 raised to a power m, times the concentration of NO raised to a power n. We say that the concentration is mth order with respect to the O2 reactant and is nth order in NO concentration. So how do we find out what m and n, the reaction orders, are? This will have to be determined experimentally by looking at the data in the table. A reaction is zero order in a reactant if the change in concentration of that reactant produces no effect. A reaction is first order if doubling the concentration causes the rate to double. A reaction is nth order if doubling the concentration causes a 2 to the n increase in rate. Note that the rate constant K does not depend on concentration, only temperature. To find out what m and n are, we will introduce you to a method called the method of initial rates. We determine reaction order by comparing quotients of reaction rates to quotients of reaction concentrations. If we look back at our table of data and we review what we defined as a rate law, we can take one rate law divided by another to find the value of m and n. This will lead to the ratio of reaction rates in trial 1, rate 1, and trial 2, rate 2, equals the ratio of the rate constants times the ratio of concentrations of both of the reactants, concentration of O2 in trial 1 divided by the concentration of O2 in trial 2, times the concentration of NO in trial 1 divided by the concentration of NO in trial 2, raised to their respective orders. Looking at this equation, we realize that a rate constant will be the same in either case, so we can cancel it out. In fact, rate constant only changes with changing temperature. So let's plug in some numbers, and we will see that we can cancel more things out. The rate of trial 1 is 3.2 molar per second divided by the rate of trial 2 is 5.8 molar per second equals 1.1 molar raised to the power m divided by 2.0 molar raised to the power m times 1.3 molar raised to the power n divided by 1.3 molar raised to the power n. 1.3 divided by 1.3 equals 1, and 1 raised to anything just equals 1. So we can cancel this out as well. This is the reason we do the trials like this, leaving one reactant constant in two different trials and only varying one reactant. Because then we can get a scenario like this where we can figure out what M and N our reaction orders are. Now our equation is 3.2 divided by 5.8 equals 1.1 raised to the power m divided by 2.0 raised to the power m. 3.2 divided by 5.8 equals 0.552, and 1.1 divided by 2.0 equals 0.55. So 0.55 equals 0.55 to the m power. Obviously, the m power equals 1, because anything raised to the 1 power equals itself. The order with respect to the O2 concentration is 1. This corresponds to our saying, a reaction is first order if doubling the concentration causes the rate to double. This is exactly what happened here. To find our order of NO, we can look at trials 1 and 3. This means our equation will look like the ratio of reaction rates in trial 1, rate 1, and trial 3, rate 3, equals the ratio of rate constants times the ratio of concentrations of both of the reactants, concentration of O2 in trial 1, divided by the concentration of O2 in trial 3, times the concentration of NO in trial 1, divided by the concentration of NO in trial 3, raised to their respective orders times the ratio of the rate constants. Again, we realize that a rate constant will be the same in either case, so we can cancel it out. We will be left with 3.2 molar per second divided by 17.0 molar per second equals 1.1 molar divided by 1.1 molar raised to 1 times 1.3 molar divided by 3.0 molar raised to the n power. Now our oxygen concentrations will cancel out, because 1.1 divided by 1.1 equals 1, and even though it is raised to the 1 power, it is still equal to 1. So now we have 3.2 divided by 17 equals 1.3 divided by 3.0 raised to the n power. So 0.188 equals 0.433 raised to the n power. To find what n is, take the log of both sides. Then we have log of 0.188 equals log of 0.433 raised to the n power. The n comes out because of the rules of logs, which states that the log of a number raised to n will equal that number times n. So therefore, n equals the log of 0.188 divided by the log of 0.433, which equals negative 0.726 divided by negative 0.364. N therefore equals 2. So the reaction is second order in NO concentration. These orders of reaction need to be determined experimentally. They are not related to the stoichiometry of the equation. Even though it looks that way for this reaction, it is not the case. To write the rate law, we now know that rate equals K times the concentration of O2 times the concentration of NO raised to the second power. We do not write the reaction order of 1 in the rate law. The overall reaction order of the reaction equals the individual orders summed, or the sum of the powers in the rate law equation. So for example, this problem that we just figured out, the overall order would be 1 plus 2, which equals 3. To solve for our rate constant, plug one of our experimental trials into our rate equation and solve for K. Let's pick trial 1. Then we will have 3.2 molar per second equals K times 1.1 molar times 1.3 molar squared. K equals 3.2 divided by 1.1 times 1.3 squared, which equals 1.7 for the value. For the unit, we need to take our molar per second and divide it by molar to the third power. For our example, the rate law constant has a unit of 1 over S times molar squared. Another way to say this is liters squared divided by moles squared times seconds. The units of K depend on the overall order of the equation and will change with different rate laws. Now we will work on some problems that use the concepts and equations discussed in this video. 1. the reaction between N2O5 and water is the source of nitric acid in the atmosphere. N2O5 gas plus H2O gas results in 2HNO3 gas. A. If the reaction is first order in each of the reactants, write the rate law for this reaction. B. When the concentration of N2O5 is 0.132 millimolar and H2O concentration is 230 millimolar, the rate of the reaction is 4.55 times 10 to the negative 4 millimolar per minute. What is the value and the units of the rate constant? For letter A, the rate law is written as rate equals the rate constant, K, times the concentration of N2O5 times the concentration of H2O. Since both reactants are first order, the one superscript is understood and not written in most cases. For part B, plug the values into this equation and solve for K, the rate constant. This will be 4.55 times 10 to the negative 4 millimolar per minute equals K times 0.132 millimolar times 230 millimolar. K will therefore equal 4.55 times 10 to the negative 4 millimolar per minute divided by 0.132 millimolar times 230 millimolar. We will cancel one of the millimolars out. Therefore, K will equal 1.50 times 10 to the negative 5, and the units will be 1 per millimolar times minute. 2. The rate of the reaction NO2 gas plus CO gas results in NO gas plus CO2 gas was determined by running the following trials at 225 degrees Celsius. A. What is the order with respect to NO2? What is the order with respect to CO? What is the overall order? B. Write the rate law expression for this reaction. C. What is the value with units of the specific rate constant, K? D. Calculate the rate of appearance of CO2 when the concentration of NO2 equals the concentration of CO equals 0.500 mole. In order to find the order with respect to the two different reactants, use the generic rate equation, which is rate equals K, the rate constant, times the concentration of NO2 raised to the unknown order m, times the concentration of CO raised to the unknown order n. To find the value of m, use two trials where the concentration of CO is constant. This is trials 2 and 3. Then take one rate equation divided by the other rate equation. We will then have 1.44 times 10 to the negative 5 divided by 5.76 times 10 to the negative 5 equals K over K times 0.263 divided by 0.526 raised to the m power times 0.413 divided by 0.413 raised to the n power. We can eliminate the rate constant K and the concentration of CO because they will both cancel out from one equation divided by another. This is because the concentration of CO is unchanging in trials 2 and 3. We will then have 1.44 times 10 to the negative 5 divided by 5.76 times 10 to the negative 5 equals 0.263 divided by 0.526 raised to the m power. We will have for our equation 0.25 equals 0.5 raised to the m. To find the value of m, take the log of both sides. Then we will have log of 0.25 equals m times the log of 0.5, or m equals log of 0.25 divided by the log of 0.5. Do the math, and you will find that m equals 2. To find the value of n, use two trials where the concentration of NO2 is constant. This is trials 1 and 2. Then we need to divide the other two trials by each other, where K and the concentration of NO2 will be eliminated because they will be constant. This will be equal to 1.44 times 10 to the negative 5 divided by 1.44 times 10 to the negative 5, which equals 0.826 divided by 0.413 raised to the n power. 1 will then be equal to 2 raised to the n power. N must be equal to 0 because 1 equals anything to the 0 power. The overall order is therefore 2, we have the 2 from the NO2 and the 0 from the CO. For letter B, to write the rate law expression, we can leave the CO out completely because anything raised to 0 will equal 1. The rate law expression will be rate equals K, the rate constant, times the concentration of NO2 squared. For letter C, to find the value of the rate constant and its units, pick a trial and plug the values into the rate law expression. We will use trial 1. Therefore, we will have 1.44 times 10 to the negative 5 molar per second equals K times 0.263 molar squared. K, therefore, equals 1.44 times 10 to the negative 5 molar per second divided by 0.069169 molar squared. K equals 2.08 times 10 to the negative 4, and the units are 1 over molar times second. For letter D, plug the values of K and the concentrations into the rate law expression to find the rate. Rate equals 2.08 times 10 to the negative 4, 1 over molar times second, times 0.500 molar squared. Rate, therefore, equals 5.20 times 10 to the negative 5 molar per second. 3. The rate of a generic reaction, A, gas, plus B, gas, plus C, gas, results in D, gas, plus E, gas, was determined by running the trials in the table below. A. What is the order with respect to A? What is the order with respect to B? What is the order with respect to C? B. Write the rate law expression for this reaction. C. What is the value, with units, of the specific rate constant, K? D. What is the reaction rate when the initial concentration of A equals the initial concentration of B equals the initial concentration of C equals 0.50 molar? In order to find the order with respect to the two different reactants, use the generic rate equation, which is rate equals K, the rate constant, times the concentration of A raised to the unknown order m, times the concentration of B raised to the unknown order n, times the concentration of C raised to an unknown order p. To find the order of the reaction with respect to reactant A, use two trials where the concentration of B and C are constant and only A is changing. This is trials 1 and 2. Then take one rate equation divided by the other rate equation. We will then have 3.5 molar per second divided by 3.5 molar per second equals 1.0 molar divided by 2.0 molar raised to the m power. The reason we can eliminate the rate constant K and the concentrations of B and C is because they will all cancel out from one equation divided by another. This is because the concentrations of B and C are unchanging in trials 1 and 2. We will have for our equation 1 will equal 1/2 raised to the m power. M must be equal to 0 because 1 equals anything raised to the 0 power. To find the order of the reaction with respect to reactant B, use two trials where the concentration of A and C are unchanging and only B is changing. This is trials 1 and 3. Then take one rate equation divided by the other rate equation. We will then have 3.5 molar per second divided by 7.0 molar per second equals 1.0 molar divided by 2.0 molar raised to the n power. The reason we can eliminate the rate constant K and the concentrations of A and C is because they will all cancel out from one equation divided by another. This is because the concentrations of A and C are unchanging in trials 1 and 3. We will have for our equation 0.5 will equal 0.5 raised to the m power. N must be equal to 1 because anything raised to the 1 power equals itself. To find the order of the reaction with respect to reactant C, use two trials where the concentrations of A and B are constant and only C is changing. This is trials 1 and 4. Then take one rate equation divided by the other rate equation. We will then have 3.5 molar per second divided by 14 molar per second equals 1.0 molar divided by 2.0 molar raised to the n power. The reason we can eliminate the rate constant K and the concentrations of A and B is because they will all cancel out from one equation divided by another. This is because the concentrations of A and B are unchanging in trials 1 and 4. We will have for our equation 0.25 will equal 1/2 raised to the p power. To find the value of p, take the log of both sides. Then we will have log of 0.25 equals p times the log of 0.5, or p equals log of 0.25 divided by log of 0.5. Do the math and you will find that p equals 2. For letter B, to write the rate law expression, we can leave the reactant A out completely because anything raised to 0 will equal 1. The rate law expression will be rate equals K, the rate constant, times the concentration of B times the concentration of C squared. For letter C, to find the value of the rate constant and its units, pick a trial and plug the values into the rate law expression. We will use trial 1. Therefore, we will have 3.5 molar per second equals K times 1.0 molar times 1.0 molar squared. K therefore equals 3.5 molar per second divided by 1.0 molar squared. K equals 3.5 and the units are 1 over molar squared times second. For letter D, plug the values of K and the concentrations into the rate law expression to find the rate. Rate equals 3.5 1 over molar squared times second times 0.50 molar times 0.50 molar squared. Rate, therefore, equals 0.44 molar per second.